Hey everybody, in 142 I am here to talk about this titration worksheet that I assigned to you last week. I am in the lab, so we may get interrupted and have some echoey things going on, but this is the only time I have to be able to work through this with you. So please excuse any interruptions that may occur. Alright, so we're starting off here with your basic titration curve. I know right from looking at this that this has got to be a weak acid titration. I didn't even read anything yet. And I know that because the equivalence point, so in other words where the pH is changing really rapidly, there's one here and there's another one here. These points are not at a pH of 7. This one looks like somewhere in the acidic range, and this one might be a little bit basic. So it tells me that I'm dealing with a weak acid here. Also, I'm dealing with what we call a diprotic weak acid, meaning it has 2 protons to lose because there's 2 equivalence points. So that's the first thing I noticed right away. And then as we read the question, we can see, so this abbreviation is correct because the A represents essentially all of this part, okay, and then the 2 H's, this one and this one, are the acidic protons that we're titrating. Okay, we have 100 milliliters of the vodka, which is our sample, that has the acid in it. So essentially we have 100 milliliters of acid, and we're titrating it with this molarity of NaOH, and it requires 11.56 milliliters to completely titrate the acid. Okay, so complete titration means the final equivalence point. So here at this point it took 11.56 milliliters. Okay, now I don't know what kind of questions are going to be asked, but I do know that it's probably a good idea to know what these volumes of base are. Alright, so at point E we have added a total of 11.56 milliliters. That means halfway through the titration we would have added half as much. Now this is a diprotic acid, 2 protons, so halfway through the titration is the point where all of the initial stuff has been converted. So this is halfway. So in order to figure out the volume here, you just divide by 2. Okay. Half of that would give us the first midpoint. Alright. So it's going to be whatever C is divided by 2. And over here at D, there's 2 ways to get there. You can either realize that 1/4 of the way through is to point B, and half of the way through is to point C. So 3/4 of the way through is going to get us to D. So you just add B and C to get D. Another approach is to realize, and this is particularly handy when I don't have to calculate the entire titration curve, like if the question is just what is the pH at midpoint 2, then all I have to do is multiply my total volume by 0.75, because at midpoint 2 we are 75% of the way done with the titration. So this just takes a little bit of logic to figure out the volumes. Alright, and I'm just going to list them here for convenience. This is volume of NaOH, I guess I should be specific. Alright, so these are the volumes we calculate for each of those points. This is volume of base that's been added, and that's going to become relevant especially for the points where we need a molarity for our calculation, which is going to be these 3. We don't actually need molarities for B and D, and the reason for that is they are midpoints, which means I can use the Henderson-Hasselbalch equation in terms of moles, and I don't need to know the volume, which is a handy place to be in. Okay. Alright, so the next question, the first question, says write out the equilibrium expression for Ka1 and Ka2. Alright, so in order to do that, we need to write a reaction. The only way to have a Ka is if we know the reaction. So first off, I'm going to use that abbreviation H2A. This is for convenience instead of writing that big, long chemical structure for malonic acid. The first Ka is going to be when we lose H+, and we do this one at a time. So we lose 1 H+ initially. This will be Ka1 in the forward direction, and then Ka2 would be if we lose the second one. So that would leave us with A2-. So that's what's happening at Ka2. So these are 2, you can write it as 2 separate ones, so it'd be this reaction here. I'm going to do this in colors. That's a great idea. So the first Ka is this reaction, right? And the second Ka is just the product of that, not the one product, not H plus. Right? So that's our second. So that's one way of figuring out where we are at different parts in the titration. Okay? And so our Ka1 would be, we'll do 2 because I made this one blue, so we're going to keep doing that. H plus over A2 minus divided by the HA minus. And then Ka1 is going to be kind of the same idea, products over reactants, but this time our products are different. Okay, so when something asks us to define an equilibrium expression, that means I need a reaction first, and then I just do products over reactants. Okay, and this is an important step because it helps us later on in our pH calculations. So midpoint and equivalence points. All right, so equivalence points are where the acid that was there has been completely reacted. So the first equivalence point happens here. And I know that's the first one because it's the first one that we come to in the titration. So as we go along adding base, this is the first one. So in other words, all the H2A that we start with here has been completely converted into HA minus. And then we continue with the titration. All the HA minus from point C to E is being converted into just A2 minus. All right, so the points where the titration, or the pH changes rapidly are equivalence points. So here's one, and there's 2. The midpoints are half of that. So if C occurs at 5.78, the midpoint for C is going to be half that, which is B. Likewise, here in between C and E, directly in the middle of that is the midpoint 2, which again is 75% of the way through the titration. So you should have your curve labeled appropriately. You should be able to do that for any titration. All right, so the equivalence points in this particular figure are C and E. Now if we had like a triprotic, you would have 3 equivalence points. If we have a monoprotic, just 1. Okay, so kind of depends on the titration. Okay, if I start with 1 liter of 1 molar acid, it wants to know how much hydrogen was reacted at the second equivalence point. Okay. So we're thinking about a titration reaction here. We're not talking about an equilibrium, okay? Because it says how much was reacted. Equilibria are not really a reaction, it's dissociation. So I'm going to write the reaction. So when we titrate, it's with NaOH in this case. So I have my malonic acid and I'm adding NaOH. When we titrate, it's an acid and a base. And so the products are going to be salt of some kind and some water. Okay, well, the water happens because one of the hydrogens in the acid pairs up with the hydroxide here. So that means I got another hydrogen I got to get rid of. So it's going to have to pair up with a second hydroxide. So I'm going to make 2 waters. And everything else that's left over is the salt. So we have 2 sodiums and 1 A. In this case, our A has a charge of 2 plus. So I have to have 2 sodium in order to balance that. Okay, so if I start with 1 liter of 1 molar acid, so I can figure out how many moles that is. It's sometimes easier for us to picture what's happening in moles, right? So I start off with 1 mole initially. By the time we get to the end, it's asking how much hydrogen ion has reacted. Well, there's 2 hydrogen ions for every A. So really this kind of question is asking how much water do you make in moles, right? And so it's a stoichiometry question. So for every 1 mole of H2A, I'm going to have 2 moles of H plus. So for every 1 H2A, I have 2 H pluses. So we would end up with 2 moles reacting at the second equivalence point. Okay, and that's because it had 2 hydrogens to lose for every H2A. Okay, and so this second question, B, what chemical species are present at the second equivalence point? So that's E. We're talking about point E here. So at the point where basically the titration is done, what we've done is converted all this H2A into this stuff, right? So at the end, you would have some sodium. You would have some conjugate, the second conjugate. And I guess we would have some water because we made a bunch of water. The only thing that is going to influence the pH is this guy, or gal, whatever. This A2 minus is a weak base, so that means it's going to influence the pH a bit, which means our pH will not be neutral. The water and the Na don't have any influence on pH. So the A2 minus is what is going to dictate our pH at point E. And that's really what this question is getting you to realize. Just think about what's there. And then it says here, at the first midpoint, so we're talking about B, that was the first midpoint. What is the relationship between HA minus and H2A? And it wants a specific answer with an explanation. Okay, so let's think about this. At the midpoint, we have taken, say, if we start with 1 mole, we convert half of that. So at the midpoint, we would have 0.5 moles. At the same time, if we're converting half of that, we're also forming this chemical. And so if I start with 1 mole, I'm going to make half a mole of this, half a mole of this. So in other words, your acid and your conjugate are equal. Okay, so the concentration of the acid and the conjugate are equal. That means this thing is a buffer with a pH that depends only on pKa, because our Henderson-Hasselbalch equation from the buffer chapter is conjugate divided by parent acid. And so if these things end up being 1, then you get the log, or the same, then you're going to get the log of 1, which is 0. So pH equals pKa if we're at the midpoint. That's a key idea. All right, question 4. This is chapter 4 all over again, specifically the stoichiometry part of it, chapter 4.6. And there's a pretty good example, and there are actually several, of titration calculations. You need to remember how to do this because you cannot do a titration problem without stoich. So it's trying to give you a hint. Dimensional analysis means stoichiometry. All right, and so the concentration of malonic acid is going to be based on our initial conditions. So let's see. Okay, so from the original question here, we are given the concentration of base and the amount of base added, and also the amount of the acid solution that was in there. So those are the key features. So I'm just going to write them again. 05120. Don't drop the zeros at the end, especially because those are significant, and titrations are very, very particular about sig figs. So we have 4 in the volume, 4 in the molarity. We better have 4 in our answer. It's also handy to have the titration reaction, which we just wrote above, right? It's a 2 to 1. You'll notice this is not an equilibrium. Titrations go to completion. That's the point. You are forcing them to make product. You don't let them be in equilibrium. Okay, so this is a handy thing to have because now I know the relationship between my acid that I start with and the base that I used. So if I can get into moles, we'll be okay. So molarity is really moles per liter, and we're not in liters, but that's okay. We can convert it separately, or you can do it in line, or you don't even really need to convert it at all, because here's a secret I did not bother to tell you in Gen Chem. If you keep everything in milliliters, they cancel. Anywho. So here we go. It's going to be the mole ratio next. So I'm in moles of OH minus at this point. I'm trying to get to H2A. So I'm going to put 2 NaOH on the bottom and 1 H2A on the top. And then I have to also divide by the volume of acid that we put in. I like to put a 1 up there just because it makes me feel like it's a real number. Okay, and some people do this as a second step. That was not 1,000. Oops. 100 milliliters of acid solution. In this case, that's vodka. So I'm dividing by that because I need to cancel the milliliters here. See? And I cancel the NaOH part in this second factor. Okay? So if we have done our conversion correctly, we should have 0.002959, and now it keeps going 3, 6, blah, blah, blah. but I only have 4 sig figs, so that is all I'm going to write. Now, if you're uncomfortable with the concept of millimoles, which is what I'm using here, milliliters instead of liters, then you can convert each of these volumes to liters and then plug them in. That will get you to the same place, so it's cool. So this is the concentration of our acid at the beginning, so that's point A. You'll notice as I do these problems, I try to relate it back to the titration curve. I try to figure out which point am I at. This will keep me from making mistakes because each point is calculated differently. Okay, so I skipped over a problem here. I'm going to get an empty slide. And so number 5 is asking us to calculate pH. You're going to have to do this on separate paper. There is not enough room on the slide or on the homework sheet to do it. Okay, so don't ever hesitate to attach other pieces of paper. It's a lot easier for me to follow that way anyway. Okay, so I'm just going to go in order, but it's okay to go A, B, C, B, C, D, whatever you feel comfortable with. On a question like this, you want a quick boost of self-esteem. So if you remember, for example, that B and D are midpoints and that pH equals pKa there, you can jump in and solve those ones first. That's fine. I'm just going to go in order for convenience. I don't want to stress you out, so I'm going to use a calming color. Okay. As if titrations aren't stressful enough, right? Okay, so in point A, that's the initial titration. By the way, in section 17.3 of your textbook, it lays out exactly how to do a titration calculation at each point. So you definitely want to look at that. This is what they call the initial pH. And they tell us there that it's an icebox problem, essentially. It's from a prior chapter, and they even reference the sections. So if you don't remember how to do these, all you got to do is look in the book, and it will link you to the knowledge you have already. All right, so in order to do this, we need a Ka. Okay, so through the magic of the internet, I am able to find this. Okay, so I don't remember what I was saying because I got interrupted, but here's malonic acid, and here's Ka1 and Ka2, so I'm just going to jot those down. 1.5 times 10 to the -3. And Ka2 is 2 times 10 to the -6. Okay, so I don't know why the negative signs aren't coming up. There we go. So at the initial pH, the thing that's present is going to be that H2A, and so the pH depends largely on this stuff. And so our Ka1 reaction is the relevant one at point A. Okay, this is usually the hard part for people to figure out, like what is actually in the titration reaction at that point. That's what's going to dictate your pH. So in the beginning, we haven't added anything to it, so we're just have our malonic acid hanging out, doing what it does. All right, and so this is dictated by Ka1. So initially, we know the concentration because we just calculated it right there. All right, that's our initial concentration. So 0.002959. You'll note I'm picking the molarity here because in a Ka, we already wrote this earlier, but so you don't need to rewrite it necessarily. In a Ka, they're bracketed, which means it's molarity. It has to be. Okay, it can't be just moles, because moles won't cancel here, so that's important. The volume, rather, doesn't cancel like it does for Henderson-Hasselbalch. Initially, we have 0 of these, so in order to come to equilibrium, this is what has to happen. Okay, so our Ka is going to equal x squared over our initial concentration. And I'm going to use the simplifying assumption here. I'm going to assume that I don't have to do the quadratic. Otherwise, it would be minus x, and I have to do the whole deal. And so all of this is equal to our first Ka because I'm talking about the loss of 1 proton. All right. I'm not going to spend a lot of time on the math. I feel like you guys are actually pretty good at that stuff. So I'm just going to do it. Alright, so I take the square root of, multiply these two together, and then take the square root, and we get 0.002101 molar is our concentration here. I have a suspicion that that is too close to this value, so my pH might not be super accurate, but because it's a logarithm function, it might not matter that much. Okay, so I suspect probably the assumption I made here with the algebra, well, I'm not doing the quadratic, might not be valid because this looks like it's probably more than 10%, but it isn't going to influence pH too much. If you're curious one day, I encourage you to go in there and figure out how big of a difference that might be. So I'm not going to go back and do the quadratic here, and I wouldn't expect you to on an exam either. So we're just going to plug it in, negative log of H plus. It says 2.6775. That's really going to be 2.68, always 2 decimal places on a pH. So at point A, our pH is 2.68. So it's a weak acid, which is, that's a reasonable value. At point B, we're at a midpoint. Yay, this one's easy because pH equals pKa. And since this is midpoint 1, I'm going to use pKa 1. Perfect. So we're just going to go the negative log of the Ka, which I just wrote down. Okay. Whoops, that's ln. Hang on. There we go. So we got a pH of 2.82. Okay, so by adding about, whoops, that's an equal sign. You can't see it because I didn't put it there. By adding a little tiny bit of base, we have moved the pH from 2.68 to 2.82. That is the power of the buffer zone. Now, as a note, anywhere in the buffer zone you can use the Henderson-Hasselbalch equation, but only at the midpoint do we simplify to ignore the other half, that other logarithm there. All right, so C. I'm going to show you how most people probably are going to solve this, and then I'll talk about why that doesn't work. Most of you are going to say, okay, at the point C, we have converted all the H2A into HA minus, which is true. That part is right. And since we started with an acid, we're going to assume it's a conjugate base. So most of you are going to write a KB like this. So in other words, forming back right to where we started. This is only going to form a tiny, tiny bit because the K is going to be pretty small. All right, and then you're going to do an ice table. Now, our initial concentration is a little bit tricky, and here's why. All right, the number of moles of HA that forms is based on the number of moles of H2A that were there. And I didn't explicitly calculate it here, but I'll do so right now. So if you broke the calculation down a bit more than I did, then you would have already had this and you don't have to redo it. But we have this many moles in the beginning. And so that means at that point I still have that many moles. But because we have added a little bit of base, the volume is no longer 100 milliliters. It's going to be 100 milliliters plus however much base you've added at point B. Okay, so I'm going to go back to my first slide. Point B, we added, oh no, I'm sorry, point C is what we're calculating. We already did B. Point C is 5.78. Okay, so here, C, 5.78 milliliters. So our volume is going to be, gosh, I guess I'll just do it right here. The 5.78 milliliters plus the 100 we started with. So we need the total volume because we're calculating the pH of the total solution, right? So the whole thing matters. And of course I got to convert that to liters because molarities are always in liters. Okay, so this is a subtle thing, but it matters, especially in a titration where you've added a lot of base. In this particular example, we don't have a ton of base, so it probably wouldn't change the pH. I think it probably would change it by like 0.01 or 0.02 if we forget to consider the volume change. So it's not a dramatic change, but it is enough to lose a little bit of credit because you're not showing your concentration calculation here. So what I get out of that is 0.002797 is our molarity. So it is a little different from our initial molarity. Okay, and then for the purposes of this equilibrium, we're starting with none of this stuff. This is not OH minus from the titration, so you got to keep it straight. When we're asking a pH question, it's an equilibrium question. And so any OH comes from either the conjugate acid or the conjugate base that's there. Okay, and so our change at equilibrium is going to be the same kind of setup as always. All right, and so this is going to be a KB because it's a base, which means I have to use the relationship here. And so 1.5, 10 to the negative 3. Oh, this is going to be a really tiny KB because that Ka is so large. Yeah, so it's 6.6, well, okay, so 6.7 times 10 to the negative 12, so it's tiny. Okay, and this KB is defined as x squared over our initial, which again is not the initial part of the titration, just the initial part of this equilibrium problem. Okay. Alright, so I'm going to solve it. Okay, so when we solve for x, we see that there's 1.366 times 10 to the negative 7 molar. That's OH minus because that's what we're solving for here. So I'm going to do POH. So that would be the negative log of that number, which is 6.86. And then to get to pH, I take that minus 4, or that subtracted from 14. So I get 7.14. Okay, so we went all the way from a 2.82 to 7.14, so that's a really dramatic increase. Okay, and I think most people are probably going to go on to D at this point. Okay, we do expect an increase because we've added base, right? So then in D, this is midpoint 2. So the pH is going to equal pKa2. And I forgot what it was already. 2.0 times 10 to the negative 6. Alright, so we get 5.70 as our pH. Well, shoot, okay, that's where people are gonna, you should have a moment where, as you're writing this down, you go, wait, that doesn't make any sense. Right here at C, we calculated 7.14. It does not make sense if we add more base for that pH to go down in midpoint 2. So that should be like a big alarm for you. What happened with C? Why is it so much higher than I would have expected? Okay, and so I'll just cut to the chase. The problem is in our assumptions, which is typically the issue. And so a lot of the time people will say to me, well, maybe the assumption here that we can't simplify is wrong. And that's possible. So then they'll recalculate it and get 7.15. Not really worth the effort. Okay, I'm really sorry. I just got interrupted, so I have no idea what I was saying. All right, but so our question is what happened at point C? And so the assumption, we could assume that the quadratic assumption might be wrong, but when you recalculate it, it's not that big of a difference. So that's not the issue. The issue is much more fundamental than that. So our initial reaction here that most people would write is treating HA minus as a base because we think of it from being the conjugate of the acid we started with. Okay, but if you remember from lecture, when we are at this point in a diprotic or even a triprotic titration, if we're at an equivalence point that's in the midst of the titration, then this stuff is what we call amphiprotic. This is normally the part where I say, what does that mean to you? So just think about that for a sec. Maybe pause the video. Try to remember what that vocab word means. Okay, it means that it can be an acid or a base. Okay, and so that's the trick to this problem in C. All right, we treated it as a base here, and that did not work. So I'm going to presume it might be an acid. And so I'm going to erase this and make some room for myself. This volume, this molarity calculation is still valid. I'm still going to use it. Okay, that's better. That's more comfortable. So if I treat this as an acid, meaning it's going to give up a proton rather than taking it, then we would be making this. Okay, that is Ka2. That's the exact same reaction that we wrote earlier for Ka2. So the value of that is 2 times 10 to the negative 6. All right, so what we're going to do to decide if an amphiprotic species is one thing or the other is just like what we did with the hydrolysis problems. We're going to compare. So the Kb is 6.7 times 10 to the negative 12, and the Ka is 2 times 10 to the negative 6. Ka is bigger, so that's the one that's going to happen, not this one. Okay, so we can actually just plop this reaction back down in there, and it's going to be the same calculation, except we're going to go with Ka, and we're solving for H plus directly. What was our initial? There it is, 0.002797 molar. Okay, so we solve for X and then plug it in to the pOH calculation. That was wrong. I meant you plug it into the pH calculation because we're solving for H plus this time. That's this one right there. Okay. So our answer here is 7.5 times 10 to the negative 5 molar. And so the pH of that, I'm just going to write X, is going to be 4.13. That makes a whole lot more sense because the pH goes from 2.82, pretty dramatic increase, to 4.183, but it's still acidic, and then to 5.70. So now the pattern makes sense. Now we could have anticipated this in a couple of ways. We could have looked at the titration curve here and seen that it is not above 7, so it's not going to be a base. And we could look at the fact that we're making OH minus and be like, wait, that's going to mean it's a pH higher than 7, which doesn't really make sense because we're not done with the titration yet. In a weak acid titration, it's only going to be above 7 at the end. Oh, speaking of the end, here we go. That'll be point E. So at point E, all of the H2A that we started with, in this case it was, how many moles? 2.959. All of that is now converted all the way, so it's 2 steps, into that conjugate. All right, so if that's true, then I still have this many moles of A2 minus, and the pH at the equivalence point is going to depend on what A2 minus does with water. So this is basically a hydrolysis problem. This one's pretty straightforward because we're all the way at the end, so we are not amphiprotic here. There's no H's to give up. It can only be a base. And so we're going to do our ice table. All right, now we got to calculate the concentration again. So it's the same numbers of moles, same number of moles, but the volume is different. It's going to be the 100 milliliters plus the 11.56 at the equivalence point, and then I'm going to divide that by 1,000. So my total volume here is that. Okay, so concentration ends up being 0.002652 molar. So that's our starting concentration for our equilibrium calculation. So I've got to keep these straight. Sometimes we do a titration reaction and sometimes it's an equilibrium. And the difference is if you're calculating pH, it's probably an equilibrium thing. If you're trying to find out moles of stuff, it's probably a titration. And they have totally different approaches. Okay, so our change is going to be minus X plus X. Oops. Okay, there. Now I got it under control. And so this is a Kb, and specifically it's the reverse of Ka2, so I'm going to write Kb2. So 2 times 10 to the negative 6. So we're going to go 1 times 10 to the negative 14 divided by 2 times 10 to the negative 6, and that's going to equal Kb2. Okay? That says negative 14, not 19. Sorry. It's a digital pen. So we get 5e to the 9, negative 9. Okay. And so it's going to equal x squared over 0.002652. We solve for x. And this is the same as we're solving for OH minus here. So I'm going to have to do that POH business. So we got 3.64 times 10 to the negative 6. That's molar. You're going to go negative log of that to get POH. Which is 5.44. And then of course we go 14 minus that to get to pH. It's 8.56. Okay, so that makes sense, right? We went from D 5.70. We should be a little bit basic because now we are at the neutralization point of a weak acid, right? So far so good. Okay. So one approach to this is to look up a bunch of KAs and calculate the pH at the midpoint, or no, the initial point. Okay. So I'm just going to make one up. So we're going to test these two. That's negative 2. I'm going to assume I have a 0.1 molar solution just for convenience, okay? And so my H plus concentration would be, now you probably would make up completely different numbers, and that's fine, it doesn't matter, but you've got to show me some evidence for why you believe the trend happens the way it does. And so the negative log of that would be 3. Now, this is a smaller Ka, right? I'm going to solve it with the same initial concentration, so we're consistent. But it's a smaller Ka, so we're decreasing as I go along. Okay. So, x minus is 0.01, x is 0.01 molar. So the pH is going to be the negative log of 0.01, which is 2. So we decreased Ka here, and pH went down. Think about that.